My name is Vivek, and today, on the behalf of my team, I'll be presenting you the time series analysis of Indian rupees to US dollars exchange rate from the year 1973 to 2024. Our goal here to evaluate how the Indian rupees has performed over the decades to assess its sustainability for the long-term investment strategies. So let's move forward and look at the data. So the data that we got here is from the Federal Reserve Bank of St. Louis. We analyze the average data exchange rate spanning over 52 years. This data being annual has no seasonal structure but capture long-term macroeconomic movement. It's structured as a univariate time series with one value per year. Let's move on to the visual analysis. Looking at the trend, there is a clear depreciation of INR over time. Major shifts are noticeable during 1991, 2008, and 2020 periods links with economic reform and global financial crisis. The variance also increased post 2020, reflecting growth volatility. Our QQ plot and Shapiro test suggest that the data is not normally distributed, so we'll transform or differentiate the data before modeling. So let's move on to the next slide. Stationary analysis. So before moving forward, we'll do the stationary check of the data to analyze whether the data is stationary or not. For this, we have done ADT test and PP test. Both of these values are greater than 0.05, which means we are failed to reject the null hypothesis, which is strongly suggested by the KPPS test. So this means the data is non-stationary. Further, the ACF shows the slow decay typically it is common with the non-stationary data, and a clear spike at PACF shows the strong autocorrelation. So overall, we can say that the data is non-stationary. So before moving forward, we'll need to differentiate the data model specification. So after differentiating the data, we tried some of the most visually obvious models that were linear and quadratic. As we can see from the chart here, quadratic model performs slightly better than the linear, but the residual analysis indicates some structure still remains, prompting the need for ARIMA models for capturing the autocorrelation most effectively. So in the next slides, we'll move forward with the ARIMA models. ARIMA modeling. To find the best fitting ARIMA model, we first did the EACF table, which suggests the ARIMA 122 and ARIMA 123. Further, we did the BIC matrix, which strongly supports that the ARIMA 112 and further on we analyze the ACF and PACF, which gives us the ARIMA 223. So further we'll run this model and do the diagnosis on the residual of these models. Parameter estimation. We estimated parameter using both maximum likelihood and conditional sum of squares. The ARIMA 122 and ARIMA 123 has no statistically significant coefficient, and thus they are the weak models. However, Rima 223 stood out and that were highly significant across models, showing the strong statistical reliability. To summarize among the model tests, Rima 223 emerged as the best performing based on the most statistically significant of its parameters and the low AIC-BIC values. It also demonstrated the best predictive accuracy with low RMSC and MEA score. However, we are not done here. Before moving forward with forecast, we plan to explore some more models to see if we can achieve a better fitting model, especially as we refine the models for the long-term projection. So far, we have established a strong foundation. We have processed the data, checked for seasonality, performed model specification, and evaluated parameter estimation. The next step is to experiment further and finalize the best possible model for forecasting. Thank you.